Welcome to the fifth session of our lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the laboratory for quantum materials and devices. We would also like to give special thanks to the NordTech Hub and the Microelectronics Commons for making this lecture series possible. In this session, we focus on one specific type of transmission line resonator, the coplanar waveguide, or CPW resonator. The CPW geometry is widely used in microwave engineering and integrated circuits, and it is especially attractive for superconducting quantum technologies due to its scalability. The objectives of this session are as follows. First, to become familiar with the coplanar waveguide geometry. Second, to describe CPW resonators. And third, to gain an understanding of two coupling methods for CPW resonators. The coplanar waveguide, or CPW, is part of the planar transmission line family, which also includes microstrip, stripline, and slot line geometries. These transmission lines are compact, easy to fabricate, and well suited for microwave integrated circuits. The CPW was first introduced in 1969 by Cheng P. Wen for non-reciprocal magnetic device applications. Its structure consists of a center conductor flanked on both sides by semi-infinite ground planes, separated by open gaps, all built on a dielectric substrate. In this lecture, we will use the following notation for its dimensions: W for the width of the center conductor, S for the width of the gaps, D for the thickness of the conductors, and epsilon R for the substrate dielectric constant. Key parameters of the line, such as the characteristic impedance, depend on the ratios of these dimensions. This makes scalability one of the most useful features of the CPW. Let us briefly discuss the wave propagation mode in a coplanar waveguide. Transmission lines with two or more conductors can support transverse electromagnetic, or TEM, waves. These waves have electric and magnetic fields entirely transverse to the direction of propagation, with no longitudinal components. This is shown in the figure on the right, which depicts the cross-section of a CPW. If the dielectric above, below, and between the conductors is the same, the CPW supports TEM waves, with the phase velocity equal to the speed of light divided by the square root of the relative permittivity of the medium. In a true CPW, however, the dielectric is not uniform. Some field lines travel in the substrate while others extend outside it. This leads to different phase velocities and introduces small longitudinal field components, so the wave is no longer purely TEM. Instead, in most practical cases, the CPW supports what is called a quasi-TEM mode. In this mode, the phase velocity is written the same way as for TEM waves, but with an effective permittivity. There are several theoretical and experimental methods to determine a substrate's effective permittivity, but these are beyond the scope of today's session. For design purposes, however, online calculators are available that provide highly accurate values for the effective permittivity of coplanar waveguides. To give you an example, the relative permittivity of silicon at 300 Kelvin is approximately 11.8. If we use silicon as the substrate for a CPW with W equal to 10 microns and S equal to 6 microns, the effective permittivity, epsilon effective, is roughly 6.4. Now let's explore the implementation of resonators with coplanar waveguides. We begin with the half-wavelength resonator, which, as discussed in previous sessions, can be realized in two ways, with open-circuited ends or with short-circuited ends. In these conceptual diagrams, both cases are shown as a CPW section of length L separated by a white gap from the ground plane. In the top diagram, the gap is continuous around the ends of the center conductor. In the bottom diagram, the center conductor is connected directly to the ground plane, creating a short. Beyond these simple diagrams, here's a real design implementation. The chip layout shows four half-lambda CPW resonators, each coupled to a common CPW feed line. The feed line is terminated at both ends with CPW launch pads, which serve as the chip's external connection ports. Arranging resonators along a shared feed line with two ports is known as the hanger mode measurement scheme. We will return to measurement schemes in more detail later in our lecture series. For now, let us zoom in on resonator number 3. At both ends, we clearly see a gap between the center conductor and the ground plane. This identifies it as an open-ended half-lambda resonator. This slide illustrates the implementation of quarter wavelength resonators using CPW. In the chip design shown on the right, we can observe that each resonator is terminated differently at its two ends. The end that is farther from the feed line is shorted, while the end that is closer to the feed line remains open. When designing CPW resonators, two key parameters must be considered: the resonant frequency of the fundamental mode, F0, and the characteristic impedance, Z0, which determines how the resonator matches to external circuits. Both depend directly on the geometry and materials of the CPW. For a TEM wave, the frequency equals the phase velocity divided by the wavelength. Therefore, for CPW half-wavelength resonators, the resonant frequency of the nth mode can be obtained by this relation, where the phase velocity is replaced by the speed of light divided by the square root of the effective permittivity, and the wavelength is replaced by 2 times the resonator length, L, divided by the resonant mode number, N. In a half-wavelength resonator, the fundamental mode occurs when N equals 1, which simplifies the expression as shown here. A similar analysis applies to quarter wavelength resonators. These equations show that the resonant frequency scales inversely with the resonator length. Shorter resonators resonate at higher frequencies and highlight the influence of the substrate and geometry through the effective permittivity. For example, let us estimate the fundamental frequency of an 11 mm long half-wavelength CPW resonator on silicon at 300 Kelvin, with a center conductor width of 10 microns and a gap width of 6 microns. As we mentioned earlier in this session, a CPW with these characteristics has an effective permittivity of 6.4. Therefore, the resonant frequency of the fundamental mode is approximately 5.4 GHz. Another essential design parameter is the characteristic impedance, Z0, because it allows the CPW to connect to other transmission lines while matching their impedances, minimizing reflection and loss. One commonly used approximation for Z0 is given by this expression. Notice that it involves the effective permittivity, so substrate selection plays a role. The formula also includes the function capital K, which is known as the complete elliptic integral of the first kind, with a lowercase argument k0, known as the elliptic modulus. In this approximation, the elliptic modulus depends only on the CPW geometry, specifically the ratio between the center conductor width and the gap width. This is powerful because we can laterally expand or shrink the CPW on the same substrate while keeping its characteristic impedance relatively the same. For example, this allows us to widen the feed line to larger connection pads, as shown on the right of this slide. In practice, designers rarely calculate Z0 manually. Instead, built-in software tools and online calculators are used to quickly determine Z0 from the geometry and dielectric properties. To make CPW resonators useful, they must be coupled to external circuits. Let us briefly discuss two common coupling methods: capacitive and inductive. Capacitive coupling is achieved through electric fields across gaps between the feed line and the resonator. This slide shows an open-ended half-wavelength resonator capacitively coupled to the feed line at both ends. The equivalent RLC model is also shown, with the two coupling capacitors labeled C sub C. This arrangement, where the resonator is placed in the middle of the signal path, is known as transmission mode. We will discuss it in more detail later in our lecture series. The figure on the right shows a real implementation of a resonator capacitively coupled to a feed line. The author illustrates two types of coupling capacitors: gap capacitors and finger capacitors. Panel D represents one of their resonators, while the close-ups in panels E, H, I, and K show 4 different capacitors they implemented in their study. I and K are gap capacitors with different gap lengths, and E and H are finger capacitors with varying numbers of fingers. By changing the geometry of these capacitors, they effectively change the coupling capacitance, leading to 2 scenarios. Small coupling capacitances produces undercoupled devices, where the energy exchange between the resonator and feed line is low, resulting in a high coupling quality factor, QC, because coupling losses are minimized. Conversely, large coupling capacitance produces overcoupled devices, where energy couples more easily to the feed line, resulting in a low QC. This concept will become really important when we discuss CPW measurements and data analysis later in this lecture series. Although capacitive coupling has been the predominant method in superconducting CPW resonators, inductive coupling has also been studied. In this example, we see a short-ended half-wavelength CPW resonator, also shorted to the feed line. The local impedance discontinuities at both ends act as shunt inductances to ground, represented in the RLC model by L sub C. On the right side of the slide, a real implementation of this inductive coupling is shown. The CPW resonator is highlighted in red in panel A, while panels C and D provide close-ups of the inductive coupling at each end. Let's recap what we have learned in this session. Coplanar waveguides, CPWs, are a class of planar transmission lines with a central conductor and adjacent ground planes on the same substrate. Their geometry, defined by conductor width, gap size, conductor thickness, and substrate permittivity, sets their electrical properties, such as resonant frequency and characteristic impedance. CPWs support quasi-TEM propagation, in which the phase velocity is equal to the speed of light divided by the square root of the effective permittivity. The resonant frequency of CPW resonators depends on its length and on the effective permittivity. Its characteristic impedance Z0 is derived from its lateral dimensions and the effective permittivity. This is usually calculated using software tools, and coupling to resonators can be inductive or capacitive, with capacitive coupling being the most common in practice. CPW resonators can be overcoupled with low QC or undercoupled with high QC. Thanks for watching, and see you in the next session.